Hello, this is the video lecture for physics for Monday, April 13th. And today what I'm going to do is go through the study guide and solve the problems for you so you can see the solutions. So we'll jump right in here. I just wanted to let you know though that the exam is on Wednesday. What I'll do is I'll post the exam on Moodle on Wednesday at 8 a.m. and then the exam itself is due at 5 p.m. So what you want to do is turn it in via email. You can either take pictures of your solutions or you can scan your solutions, and I will turn around and grade that as soon as possible. I do apologize, I'm behind on grading, so what I'm going to do so you have your homework to use to study is as soon as I finish this video exam or this video exam review, then I will grade homeworks 22, 23, and 24, get those back to you today, as well as physics test 2. So hopefully that'll bring us up to date so you have enough information for homework. So anyhow, the first problem, we have a resistor and it cannot exceed 14 watts power. So we have our resistor here. We have current going through, so this is 17 ohms. And we know that P max is equal to 14 watts. Okay, so let's go back and look in our book for the governing equations for this. Okay, I'm going to try my best to show these equations in the book for you. So we know, bring this way over here, the power is equal to I times delta VR over the resistor, or we can say that that's I squared R, which is probably the easiest form of the equation to use. So we have resistance, we know power, and then we can calculate I squared and then I, which is current. Okay, so we'll go ahead and do that. If my DocCam will cooperate. Okay, so we know that power for the resistor is equal to I squared times resistance. So I is just going to equal power divided by resistance, take the square root of it. Okay, and so that's 14 watts divided by 17 ohms to the 1/2 power. Do that. My calculator here. Go ahead and put it in its full mode here. Okay, so 14 watts divided by 17 ohms equals, and then we take the square root of that, and that gives us 0.907 or 0.91 amps is our maximum current. Okay, so that's pretty straightforward. So you're just using something from the book there. The second problem, we have the resistivity of gold at a temperature of 20 degrees Celsius. We have a gold wire and it's 0.5 millimeters in diameter, and it is 44 centimeters long, and it carries a current of 380 milliamps. Okay. So we know what the current is. We know the dimensions of the wire. So we know the cross-sectional area of the wire. And then we can find how many electrons are going through at a given point in time. So for this problem, we have kind of an odd situation. They give you a lot of information that you don't need. Because we know that current I is equal to delta Q over delta T. So we know the change in charge in coulombs divided by the change in time, seconds. A coulomb per second is an ampere, and so that's how we measure charge. Okay, so let's go back to the original problem statement. Okay. So we're given the current already. So we know that I is equal to delta Q over delta T. So that is equal to 380 millicoulombs divided by 1 second. Okay. And we know that an electron is equal to 1.6 times 10 to the negative 19th coulombs. Okay, so if we want to know electrons per second, then we just take this value up here, and we know that 1 electron is equal to 1.6 times 10 to the negative 19th coulombs. Okay. Okay, so coulombs cancel. So let's put this in actual coulombs instead of millicoulombs. I'm just going to put a point right here. Okay, then we plug this into our calculator. Okay, so we have 0.380 milliamperes, which is actually 0.380 amperes, which is 0.380 coulombs per second divided by 1.6 divided by 10 to the negative 19th. And that gives me 2.4 times 10 to the 18th electrons. Electrons per second. Okay, so I just described that like that. Oops. And that is my answer. Okay, so moving along. I've done 3 problems for each chapter here, so you probably only have 2 problems per chapter on your test, but I wanted to give you some additional examples just so you could get as much information as possible. Okay, so the third problem is that I have a 120 volt toaster, and it has nichrome wire with a length of 5.4 meters and a diameter of 0.48 millimeters. The resistivity of the nichrome at operating temperature is 1.3 times 10 to the negative 6 ohm meters, and it's operating at a voltage of 120 volts. So the power drawn is just going to be the voltage times the current. Okay, so we know voltage is 120 volts. Okay, and now all we have to do to find the current is just take that voltage divided by the resistance of the toaster. Okay, so we need to know the resistance of the toaster is equal to the resistivity. Okay, and we'll go ahead and look this up in the book so you can find the equation. Okay, where's my resistance? Okay, there we go. Sorry about that. So the resistivity is equal to, the resistance is equal to the resistivity times the length of the wire divided by the cross-sectional area. So we can go ahead and plug that in. Okay, let's see if we can do this without tipping over. Okay, so the length of the wire divided by the cross-sectional area. So we're given the resistivity here as 1.3 times 10 to the negative 6 ohm meter. The length of the wire is 5.4 meters. And the cross-sectional area of the wire is 0.00024 meters. Okay, just taking half of the diameter of the wire, take the square root of that, multiplied by pi, and that gives me the resistance at the toaster. So we take 1.3 times 10 to the negative 6, okay, times 5.4, which is the length, divided by 0.00024, which is the radius, squared, divided by pi. And that gives me about 38.8 ohms. Okay, now we can find the current in the resistor. It's going through the resistor, just 120 volts, divided by 38.8 ohms. So that gives us a current of 3.1 amps. Okay, and then our power, which is just our current times our voltage, is 3.1 amps times 120 volts. Whoops. Is 372 watts. Okay, so a 372 watt toaster. Okay, so let's move on to the next problem. So here we have a current, or a circuit, and we have two resistors, and another two resistors in parallel. So we have these two resistors here, and we have these two resistors here. Each resistor is 600 ohms, and we want to know the equivalent resistance of the circuit. Okay. So there's our circuit. So we have 600 ohms on each one of these. So what we're going to do is we'll do an equivalent resistor here, and we'll do an equivalent resistor here. Okay, so this equivalent resistor is 1 over 600 plus 1 over 600 to negative 1 power. So that gives us 300 ohms. This resistor over here, we'll call REQ2, is 1 over 600 plus 1 over 600 to negative 1 power, which is also 300 ohms. Okay, so that's kind of interesting and a little redundant, but we take REQ for the first one, and we take R plus REQ for the second one. They're now two resistors in series, and REQ total is equal to 300 ohms for the first one, plus 300 ohms for the second one, and that equals 600 ohms. So all we've done is we've created a circuit of equivalent resistance of 600 ohms, and that's it. Okay, so that's all you need for problem number 4. Problem number 5. We have a 2 ohm resistor here. We have a 1 ohm resistor here. We have a 5 ohm resistor here. We have a 1 ohm resistor here. And we have a 4 ohm resistor here. Okay, so we want to know what's the power dissipated in the 2 ohm resistor. Okay, so there's a really easy way to do this, and that is that we just use Kirchhoff's voltage law. And if a 12, I'm gonna put my battery over here, 12-volt battery. No, it's going the right way, yes, okay. Okay, so there's, the easy way to do this is to first figure out the equivalent resistance of this entire circuit, okay? So you can find the current that is going through this point here, I. Okay, that current splits into I1 and I2, okay? So we're going to use Kirchhoff's voltage law to tell us how the current splits. And then once we know the current going through the 2 ohm resistor, then we know that power is just I squared times R. Okay, so first of all, we find equivalent resistance. So here, this is equivalent of 3 ohm resistor here, and this is equivalent of a 6 ohm resistor here. Okay, so REQ in this case is 1 over 3 ohms plus 1 over 6 ohms, take to the negative 1 power. And that is just an equivalent resistor of 2 ohms. Okay, so then the equivalent resistor for the circuit, or total, is 2 ohms plus 4 ohms. That gives me 6 ohms total. And the current in the circuit is just the voltage divided by the equivalent resistance total. That's 12 volts divided by 6 ohms. So that gives me 2 amps. Okay, so now I know up here, okay, can you see? No, I can't see that. Okay, move that around. There we go. Okay, so here I have 2 amps and it's splitting in 2 directions. In this case, it sees 3 ohms of resistance. In this case, it sees 6 ohms of resistance. Okay, but I know my equivalent resistance over here. The equivalent resistance here is just 2 ohms. Okay, so the voltage over this total element is just the current going in by the equivalent times the equivalent resistance. So that gives me 2 amps times 2 ohms So I know that I lose 4 volts over that equivalent circuit. So I've lost 4 volts over that equivalent circuit. Okay, so if I lose 4 volts over here, then I know 4 volts divided by 3 ohms equals 1.33 amps. Okay, so that's I1. I1 is 1.33 amps. The resistance is 2 ohms. So if I want to know the power, remember the original question was to find the power disseminated, or power that is dissipated. Okay, so that would be equal to I squared, I1 squared, times the resistor. So that's equal to 1.33 amps, quantity squared, times the resistance, which is 2 ohms. Take that. And I get 3.54 watts dissipated in that resistor. Okay, so that's problem number 5. Let's move down to problem number 6. Okay. Okay, just for maximum confusion, this is on 2 pages. I'll try to get both pages on here. So I have a circuit up here, and initially the switch is open and the capacitor is uncharged. So I close the switch at time t equals 0. And in the figure shown, I want to know what the charge is of the capacitor in microcoulombs after 8 seconds. Okay. So 70 volts, a switch, it's open, a 90 microfarad capacitor, and a 0.2 mega ohm resistor. That is a ghetto drawing if I've ever seen one. Okay, so 70 volts here. Okay, and the resistance is 200,000 ohms. Okay, so let's look for the equation in the book for capacitance and resistance. We're charging, okay, we're not discharging, we're charging. So we're going to chapter 23. So we're looking at R circuits, RC circuits. And we're looking at not at discharge, but at charge. So we know that when you charge a capacitor, that the voltage across the capacitor is equal to your potential of your electricity source times 1 minus e to the negative time divided by RC. So we can find the voltage in our capacitor. Okay. So we go ahead and do that. Okay, so we can plug in numbers there. So we know we have 70 volts, 1 minus e to the quantity, 8 seconds, divided by 90 times 10 to the negative 6 farads, also divided by 200,000 ohms. Okay. Yeah, it looks like 190, but that's a parentheses. So 90 times 10 to the negative 6 farads times 200,000 ohms. Okay, so we go ahead and plug that in. Let's just take the equations one chunk at a time. Okay, so first we have 8 seconds divided by 90 divided by 10 to the negative 6 divided by 200,000. Okay, then we take the negative sign for that. And we take the natural log function. Okay, we take the negative of that plus 1. Then we times 70 volts. Okay, so at that point in time, our charge in voltage is now 69.18 volts. Okay, unfortunately, that's not what the problem is asking for. We actually need to know the charge on this individual side of the capacitor. So we need to know what Q is, and we need to relate Q to voltage. Now, we have to go back to chapter 21 in order to understand what charge is related to voltage, but it turns out that Q, charge, is just equal to capacitance times delta voltage for the capacitor, okay? And so our capacitance is 90 times 10 to the negative 6 farads. Our voltage is 69.18 volts, okay? And that gives us 0.0062 coulombs of charge, okay, that's accumulated on that capacitor. Okay, so that's the answer for number 6. Okay, so moving on, I have to get my paper here really soon. So now I have number 7. Okay, so we have an alpha particle. Its charge is 2 times electrons. Its mass is given there. Okay. And a number 7, the figure is for number 8. The figure is not for number 7. Okay. The magnetic field in the cyclotron is 0.8 Tesla, and the orbit radius is 0.3 meters. So we want to find the period for that particular alpha particle. Okay, so it turns out that in this particular problem, the period is 2 times the radius divided by the velocity. But we know the radius already. All we have to do is calculate the period t is to get the velocity. So it also turns out that the force is just the mass times the velocity squared divided by the radius. which means also that the radius is equal to the mass times the velocity divided by the charge divided by the magnetic field. Okay, so we can back calculate velocity from this. We'll just go ahead and rearrange this. And velocity is equal to R times Q times B divided by the mass of the particle. Okay, so we just move down here. The radius is 0.3 meters. The charge is 2 times an electron, only it's a positive charge. Okay. The magnetic field is 0.8 Tesla. And the mass is 6.68 times 10 to the negative 27th kilograms. Okay. We just multiply that out. Move this up a little bit. Just multiply that out. And what I get for this velocity is ultra high. Let me go ahead and recalculate that again. That just seems a little too high to me. Okay, I've got the charge, radius, 2 times the charge times the magnetic field divided by the mass. Okay, I'm gonna try that one more time. It just seems like a lot to me. It's like exceeding the speed of light, which kind of bugs me. Okay, 0.3 times 2 times 1.6 times 10 to the negative 19th times 0.8. My numbers are looking better already. So for this and a cyclotron, I get 1.1 times 10 to the 7th meters per second. Okay, that makes me so much happier. I was getting a different number and it didn't make me happy. So I just then plug this into the period here. Period T is equal to 2 pi times 0.3 meters as our radius divided by our velocity 1.1 times 10 to the 7th meters per second. Meters cancel, and that gives it seconds. So I'll just go with my number here. Take the reciprocal of that, times 2 times pi times 0.30, and that gives me 1.6 times 10 to the negative 7th seconds. Okay, so it's spinning around really fast already. Okay, now, next problem. So we have a rigid rectangular loop. This is one of these niggly torque problems. Okay, it's 0.3 by 0.4, and it carries a current as shown. A current is going clockwise, 5.5 amps. The external magnetic field has a magnitude of 2.9 Tesla in the negative x direction. And segment CD is in the x plane, xz plane, and it forms a 35-degree angle with the z-axis as shown. So we want to know what is the magnitude of the external torque that keeps us in equilibrium. Okay, so first of all, we need to know what torque is being applied by this magnetic field. Okay, so to do that, then we know that the torque is equal to the current times the cross-sectional area, whoops, right back down there, times sine of alpha. Okay, alpha or sine theta, and theta is the direction in which it is askew from being perpendicular to the magnetic field. Okay. So in this instance, we know our current, that's 5.5 amps. We know our cross-sectional area, that's just 0.3 meters times 0.4 meters. Okay, let's show this way down on the page. Okay, so I have my current, and I have my cross-sectional area here. And then theta in this particular loop here then we're looking at this going in the negative x direction. So we extend our x-axis back there. And if we look at what angle this is placed in light of our negative x direction, it would actually be 55 degrees. Okay, so I wanted, even though it's 35 from that xz, from the z-axis, that's actually 55 from the direction of the magnetic field. Okay, so make sure you understand that. So we go ahead and plug in numbers there. So we have 55 degrees, take the sine of that, times 0.4, times 0.3, times 5.5, and that gives me a torque of 0.54 Newton meters. Okay, so in order to keep that stationary and oppose the torque, then I would have to have the same torque applied in an opposite direction. Okay, and so this asks what's the magnitude of the external torque, and the magnitude of the external torque is 0.54 Newton meters. Okay, and then finally we have number 9. Okay, coming down the home stretch here, number 9. So we have a wire that is carrying current in a circular loop. I don't know why this isn't focusing. Sometimes it tries to focus on something else and it won't focus on the print. Let's see if I can get that to focus on the print. Okay, better. Okay, so we have a wire carrying a current and it's a circular loop of radius 4 millimeters. If the magnitude of the magnetic field at the center is 1.1 millitesla, and there's no external magnetic fields contributing to it, we want to know the magnitude of the current carrying wire. Okay, so I have a wire that's like this. Okay, I had a lot of curved coffee and it's not really working today, and I've got a field going through it that is 1.1 millitesla. Okay, and my radius is 0.004 meters. Okay, millimeters. So we go ahead and we look at inducing currents from magnetic fields. Okay, so we know that the magnetic field B is equal to the permissivity times the current times 2 pi r, which is the radius. Okay, get this in focus. This thing will cooperate with me. Okay. Okay. So our current then is just going to equal B times 2 pi r divided by the permissivity constant mu. Okay, so we can just plug in numbers. Our magnetic field is 0.0011 Tesla. Okay, just converted for that from millitesla to Tesla. Okay, times 2 pi times the radius, which is 0.004 meters, divided by mu, which is 1.257 times 10 to the negative 6 Tesla meters per amps. Okay, and then way down in the corner, we can calculate the answer. And that gives me 22 or 21.99, but I'll just call it 22 amps. And we see up here, meters cancel, Teslas cancel, and that leaves amps in the numerator. Okay, and that concludes the test review for exam 3 for physics. Like I said, I will post the exam on Wednesday at 8 a.m. and you'll have until Wednesday on 5 p.m. to email me back your test answers. Please work independently. It is open book and open notes.